Dear students, you must be familiar with various principles of chemical thermodynamics which relates thermodynamics to phenomena like chemical equilibria and chemical reactions. Now in this video, I shall introduce you to yet another principle which is related to open system. Now that is partial molar quantities. Now in thermodynamics, particularly thermodynamic properties of a system, we come across two properties, that is intensive property and extensive property. Now, extensive properties are those properties which depend upon the quantity or size of matter present in the system, while intensive properties are those properties which are independent of the quantity or size of the matter in the system, like our temperature, pressure, viscosity, etc. are intensive properties, while extensive properties which depends on the quantity of matter present in the system are entropy, enthalpy, internal energy, Gibbs free energy, mass, volume, etc. You are also familiar with the term closed system and open system. Now in closed system, there will not be any change in the mass of the system, or there will not be an exchange of matter. There will be only exchange of energy or heat between the system and the surrounding. And the change of state in a closed system is due to the variation of temperature and pressure only, isn't it? So the extensive property will be a function of number of temperature and pressure of the system and nothing else. But if we take the open system, in open system there will be an exchange of matter and energy between the system and the surrounding. So the number of moles of the components in the system may change, and hence there will be change in the mass of the system. And the change in the state will be due to change in temperature, pressure and the number of moles. In closed system, the change in state was due to change in temperature and pressure, while here it will be change in temperature, pressure and number of moles. And the extensive property will be a function of number of moles of various components of the system, along with temperature and pressure. So for an open system, we can write that the extensive property X is a function of temperature, pressure, N1, N2 up to Nj, that is N1 and N1, N2, Nj are the number of moles of the various components. So if you have a two-component system, X will be a function of temperature, pressure, N1 and N2, that is the number of moles of component 1 and number of moles of component 2. If your system has a J number of components, then the extensive property will be a function of temperature, pressure and the number of moles of every component from 1 to J. So that is what is meant by this equation. X is equal to function of Tp, N1, N2 up to Nj. It is related to this that we are going to discuss. So since the extensive property is dependent on or is a function of number of moles of the component in the open system, we have to consider those two. So we have this equation. Now a change in the property of X, that is dx, when the temperature, pressure and number of moles will change, will be an infinitesimal change, okay, will be dou X by dou T. Pressure, that is you are keeping the rest constant, okay, you are changing the temperature with respect to temperature, the change in property with respect to pressure, change in pressure. So you can see here in the first term we don't have temperature, we have the rest constant, pressure and number of moles constant. In the second term, that is in the pressure term, we have temperature and number of moles constant. Now you come to the third term, dou x by dou n1 into at T, N2, N3, etc. constant. That is, you are changing the number of moles of the first component. The rest are constant. Similarly, the next term, dou x by dou n2, T, N1, N3. You are keeping N2 constant. N2 is a variable while the rest are constants. So this equation will be representing the change in property of x with respect to various quantities of the system. Like this particular first term relates to the change in the property with respect to temperature, the second one with respect to pressure, the third one with respect to the number of moles of component 1, the fourth one with respect to number of moles of component 2. Then you can write for dou x, third component, dou x by dou n3, when Tp, n1, n2, n4, etc. are constant. Now the quantities dou x by dou n, that is the third term onwards in the above equation, they are called the partial molar quantities or partial molar properties of the components because they are related to the number of moles of the components. Okay, so dou x by dou n are called partial molar quantities or partial molar properties of the components. So if we write dou x by dou ni, Tp, n1, n2, etc., it is called the partial molar property x bar I of the ith component. Okay, so that is you are changing the number of moles of the ith component. So you can put it like this: x bar I is equal to dou x by dou ni at constant temperature, pressure, N1, N2, etc., etc. So this becomes a general equation for the partial molar property. Any partial molar property, like you can have partial molar Gibbs energy, partial molar entropy, partial molar enthalpy. All those properties, all those extensive properties. Instead of x, you can have all those extensive properties. So you can say that the partial molar property of a thermodynamics system shows an extensive property of a solution or a mixture. How the extensive property of a solution or a mixture changes with the change in the molar composition of the solution while keeping the temperature, pressure constant. Okay, so the partial molar property may be defined as a thermodynamic quantity. It is a thermodynamic quantity which shows that an extensive property of a solution or mixture changes with the change in the molar composition. So that's it. If you have an extensive property x, how is it changing? How is it changing with respect to the number of moles of the ith component of a component? So that is how it changes with the change in the molar composition of the solution or the system while the temperature, pressure, etc. are constant. So if you take x bar 1, then it will be x bar 1 equal to dou x by dou n1 Tp, n2, n3, n4, etc. Okay, so I stands for the number of the components, or which component you have. Now, this partial molar quantity or property is a partial derivative of the extensive property with respect to the amount of the component of interest. So that's another way of explaining this particular equation or this particular expression. It is a derivative, partial derivative of the extensive property, whichever extensive property you are considering. And it is with respect to a particular component, amount of a particular component. Okay, so that means each extensive property of the mixture has its own partial molar property, and that extensive property depends upon the molar component of the system. I mean, ith or depends upon the component, all the components of the system. Okay, so now we have partial molar Gibbs energy. Gi bar is equal to dou G by dou Ni, Tp, N1, N2, etc. We can have partial molar internal energy, Ui bar. You can have partial molar enthalpy, delta H bar, Hi bar, partial molar entropy with respect to the ith component, Si bar, partial molar volume with respect to the ith component, Vi bar, etc. So, a partial molar quantity for a given component of a system is the increase, or you can say change, in the property of the system from the addition of 1 mole of that particular component at constant temperature and pressure to such a large quantity of the system that there is no appreciable change in the concentration. So, what does this mean? The partial molar quantity for a given component of a system. So you can say that if you take the Gibbs energy, the partial molar Gibbs energy, okay, of a component, say if you have a system A containing two components A and B, you consider component A, then Ga bar means the partial molar quantity of, or partial molar Gibbs energy of the system, okay, when the component A is changed. It can be, if you are increasing the number of moles, it will be increasing the property, okay. So here we are mentioning increase the property of the system from the addition of 1 mole of that particular component. You are increasing component A. Then what will be the change in G? That is what is shown by partial molar Gibbs energy. You are keeping the rest constant. You keep all other components concentration constant and also the temperature and pressure constant. Okay, and when you change this concentration or quantity of one component, the net concentration of the whole system is not changing. There is no appreciable change. Okay, then you get the term partial molar quantity. Now, the quantity Xi bar, which represents the actual value of X per mole of the ith component of the system. Okay, so if you have Gi bar, it represents the actual value of G per mole of the ith component. Alright, so this value may be same or different from the actual molar value in the pure state. So when you mix it up, the value may be same or it can be different from that of the pure state. So if you have a system containing A and B, Xa bar can be same as that of the pure A, Xa, or Xa bar can be different from the value of Xa. Now that depends upon the interaction between A and B. Now these two values, that is partial molar value and actual molar value, are same in the case of ideal system. That is, Xa bar will be equal to Xa in ideal system. While in non-ideal system, there will be difference because of the interaction between the constituents. So the actual molar value gets modified to partial molar value. Now this partial molar value may not be same throughout the whole solution, since the extent of interaction will vary, okay, according to the amount of the constituent in the system. So the partial molar value is dependent on the composition of the system. So you can say if the system is dilute solution, if the solution is very dilute, probably the partial molar quantity will be same throughout the system. But if it is a highly concentrated system,
then the partial value may be different from will not be the same in the whole of the solution, because the interaction will change. The interaction between the components will vary. Now, therefore, the partial molar quantities are meant for the individual components of the system. But their values are not only dependent on the nature of the particular component, but also the nature of amount of the other component, because that decides the interaction. Okay, so you cannot put the partial molar quantity of a particular component as the property of the whole system. But the partial molar quantity of an individual component is dependent on the nature of that component, that's quite sure, but also on the nature and amount of the other component, because the nature and amount of the other component decides the interaction of other components with the component under consideration. So these are few facts related to the partial molar quantity, okay, which you must keep in your mind to understand the concept further. Now we have this equation, the differential equation. The equation for the change in the extensive property X with respect to various properties, like various components of the system. Now here, if we impose the constraints, that is, if we say that temperature and pressure are constant, then dt and dp will be 0. Then, that is, there is no change in pressure and temperature. Then the first two terms with related to temperature and pressure, that is change in extensive property with respect to change in temperature, and change in extensive property with respect to change in pressure, will be 0. So these two terms will be 0, since dt and dp are 0. Therefore, our equation will become dx at constant temperature and pressure is equal to x1 bar dn1 plus x2 bar dn2 plus x3 bar dn3, etc. That is change in extensive property with respect to component 1, change in extensive property with respect to component 2, etc. Because we are considering temperature and pressure constant. Now this, on integrating this equation, we can write it as x at constant temperature and pressure is equal to n1 x1 bar plus n2 x2 bar, where n1, n2, etc. the number of moles of component 1, 2, etc. Alright, and x1 bar, x2 bar are the extensive property, whichever extensive property you are considering for that particular component, for the respective component. So if you are considering Gibbs free energy, then it will be G Tp equal to N1 G1 bar plus N2 G2 bar, etc. Alright, so the partial molar value xi bar of a specified property x for the ith constant of the system is equivalent to the contribution per mole made by that constituent to the total value of x. So you can say that the total value of x for a given system is due to the contribution of the x of all the components of the system. Okay, but if we say delta G, or the Gibbs free energy is a collective property or a collective value of each of G of each component. Alright. Now, but here you keep the temperature and pressure constant. Now let us take partial molar Gibbs energy to be more clear. Now, you can call it as partial molar free energy, or it is also called as chemical potential mu I. Okay, so partial molar Gibbs energy can also be called as chemical potential. It can also be called as partial molar free energy, and it is represented as Gi bar or mu I. Now we have this equation the expression Gi bar equal to, or mu I equal to dou G by dou Ni, constant at constant temperature, pressure, N1, N2, etc., etc., changing only the number of moles of the ith component. So the chemical potential, or you can define the chemical potential, is the change in the free energy of the system, which results on the addition of 1 mole of that particular substance to a very large system, such that the overall composition of the system does not change and the temperature and pressure are constant. So this is what we have said earlier also, just explaining it again and again for you to understand it. I mean, the concept must be clear. So chemical potential is a change in free energy of the system, okay, which results due to the addition, or you can say change in the component of a particular component, change in the concentration or change in the amount of a particular component. But overall, there will not be any change in the overall composition of the system, because the system is quite large. So this infinitesimal change of the composition of one particular component is not going to affect the overall composition of the system, and you're keeping the temperature and pressure constant. Alright. Now when we keep temperature and pressure constant, we have dt and dp will be 0. Then the free energy change will be dg at constant temperature, pressure, g1 bar dn1 plus g2 bar dn2, what we have written earlier for the general case. And if we can also write it as mu1 dn1 plus mu2 dn2, if you are using the term mu, that is for the chemical potential. And you can also write it as, by integrating, you get GTP is equal to mu1 n1 plus mu2 n2 plus etc., or n1 mu1 plus n2 mu2, like that. So the chemical potential may be defined as a contribution to the total free energy of the system by 1 mole of each component of the mixture, while keeping the temperature and pressure constant. So it is the contribution, chemical potential is the contribution to the total energy of the system, total free energy of the system, by every mole of every component. And the Gibbs free energy of the system will be the sum of the chemical potentials of each individual constituent. Okay, so that is it. That you try to remember this sentence also. Gibbs free energy of the system is the sum of the chemical potential, a sum of the chemical potential of the individual constituents. So every individual constituent will be providing or will be contributing towards the Gibbs free energy, and that contribution is called the chemical potential. So you can say that the chemical potential is an intensive property, but Gibbs free energy is an extensive property. Okay, chemical potential is independent of the quantity of the material, quantity of the component. But Gibbs free energy is dependent on the quantity of the component, because Gibbs free energy is decided by the contribution of every mole of the component, while chemical potential is independent of the quantity of the component. So chemical potential is an intensive property, while Gibbs free energy is an extensive property. Now, keeping this in mind, we need to derive an equation, Gibbs Duhem equation. Now, Gibbs Duhem equation helps us to understand the partial molar quantities better. Gibbs Duhem equation can be, or you can extend that equation to all extensive properties. Now we shall be discussing, or we shall be deriving Gibbs Duhem equation with respect to the Gibbs free energy. Now particularly this is quite useful to discuss the thermodynamic concepts of mixtures. Now we have this equation, almost we'll be repeating this again what we had done earlier. That is, G will be a function of, Gibbs free energy will be a function of temperature, pressure and the number of moles of every component. And the change in Gibbs free energy with respect to each factor can be written like this. We have written it earlier. We have discussed about this earlier. And then taking, we can consider dou G by dou N1, that is from term 3 onwards. That is the change in Gibbs energy with respect to the number of moles of every component. You can put it as mu1 dN1 plus mu2 dN2, etc. So our equation 2 gets converted, or you can write it as equation 3 in this way in terms of chemical potential. Now when you assume dt and dP equal to 0, that is when you're considering the system at constant temperature and pressure, our equation 3 gets changed to this way, to equation 4, dg constant Tp equal to mu1 dN1 plus mu2 dN2, etc. And then integrating, you get gTp equal to mu1 N1 plus mu2 N2, equation 5. So all these we have done earlier, but this is the way how we derive Gibbs Duhem equation. Now when you take the total differential of this equation, you get dg equal to mu1 dN1 plus N1 d mu1 plus mu2 dN2 plus N2 d mu2, etc., etc. You are taking the total differential of this equation. Now what you can do is you can segregate this differential factors, differential terms. That is differential of chemical potential together and differential of number of moles term together. That is, all the terms which comes as dN1 will be put together, and the other one which comes as d mu1 will be put together. So you get dg equal to mu1 dN1 plus mu2 dN2, etc. plus N1 d mu1 plus N2 d mu2, etc. So that is our equation 7. So we have the equation 7 here. Now earlier in equation, we have, you just see if you compare equation 7 and compare equation say 4. So equation 4 says dg equal to mu1 dN1 plus mu2 dN2. And equation 7 says dg equal to mu1 dN1 plus mu2 dN2, etc. plus N1 d mu1 plus N2 d mu2. So when you compare equation 4 and equation 7, you can say that, you can put the second term in equation 7, that is N1 d mu1 plus N2 d mu2, etc. You can consider it as 0, right? So you have equation 7 here, equation 4 here. See, the first term in equation 7, the first cluster in equation 7 and the equation 4, they are the same. So the second cluster must be 0. So when you compare equation 7 and equation 4, N1 d mu1 plus N2 d mu2, etc. must be 0. Now this concludes that at constant temperature and pressure, the system has definite composition. So you can put it as summation N1 d mu1 equal to 0. That is, all this, this cluster will be equal to 0. Now this equation, this expression is called the Gibbs Duhem equation. Now this is with respect to the chemical potential. Now you can extend this to the rest of the other extensive properties. So you can put it as summation Ni d xi bar equal to 0. If it is entropy, it will be Si bar. If it is enthalpy, it will be H bar. If it is internal energy, it will be Ui bar, etc. So the significance of this Gibbs Duhem equation is that the chemical potential, we are talking with respect to chemical potential, the chemical potential of one component of a mixture cannot change independently of the chemical potential of other component. That means, say if you have two components A and B, then the chemical potential of A cannot change on its own. It cannot change independently. If A changes, then automatically the chemical potential of B also changes. That is what this means. So it will be clear if we take the two component system, see 1 and 2, then your equation will be, the Gibbs Duhem equation will be n1 d mu1 plus n2 d mu2. Now you can write this as n1 d mu1 equal to minus n2 d mu2. So you change chemical potential mu1 of component 1, then automatically the mu2, the chemical potential of component 2 also changes. So the chemical potential of one component of a mixture cannot change independently, cannot change on its own. You can rewrite this equation again, d mu1, change in chemical potential of component 1 equal to minus n2 by n1 d mu2. Okay, so it depends upon the ratio of the number of moles of each component. Alright, so you can say that the variation of chemical potential of one component of the system can bring variation of chemical potential of the second component of the system. You can say variation in the chemical component of one component will change the chemical potential of the rest of the components of the system. So they will change. One variation of one, if it is entropy, the variation of entropy of one component will change the entropy of the rest of the components in the system. So that's the significance of Gibbs Duhem equation. This is what we can deduct, or we can conclude from Gibbs Duhem equation. So derivation of Gibbs Duhem equation is very important. Now in the next following videos, we shall be applying this to discuss about ideal system, non-ideal system, etc. Alright, so understand the concept of partial molar quantities, and also try to understand and derive Gibbs Duhem equation. Hope this concept is clear to you. If you have any clarifications, you can please feel free and discuss with me. Thank you.